let us begin in just a minute or two. Hello, everyone. Just running about a minute or two behind, because when you teach from home, you gotta take the dog out, you know? Yeah, it is definitely morning for me. So what should we talk about today? Let's do a little bit of announcements first. That'll wake me up. See. All right, cool. And also that'll give other people a chance to find links. In the future, what I'm going to do is I'm going to leave these videos public. Yeah, I just posted the link just a little bit ago, so we'll see if more people join. I'm going to leave these links public, basically in secret. And then hopefully what will happen is that people will come to the video, and then I will move it into the playlist that's posted on the yeah, look, it's not so bad. We'll get 20 people, which is probably half the class. So, plus today if everything goes right, today should be a fun day. Because we'll talk a little bit more about tree deletion, maybe. We'll talk a little bit more about, and then we'll talk about AVL trees. So, it could be a fun day. So I'm gonna try this. So, so that people have a better chance of finding it. So today, we should do some kind of maybe tree deletion code, maybe some even coding. And then we're going to talk about AVL trees, which is more like AVL trees. I have the Wikipedia article up so I can spell their names. Adelson Velsky. See, it's one of these. It's one of these hyphenated Russian names. It's like the in mathematics there's something called the Birch-Swinnerton-Dyer conjecture, but and everybody, the fact is that Swinnerton-Dyer is just one dude. So, like Birch gets almost a single syllable, and Swinnerton-Dyer gets the rest of the, conjecture's name. So it's the same thing with AVL. AVL is two people, Adelson Velsky, which is one person, Georgy, and then Yevgeny is, I guess, probably Yevgeny or something, right? Something. Not going to really try to write Russian after I've, been awake for 10 minutes, but whatever. Okay, it looks like we have some people here. Just as a reminder, Project 1 is due in 1 week. So what that means is that you should get help from me, you should try to figure it out, all that stuff. I have that lecture where I forget which lecture it was. I think it might have been the previous lecture or maybe the one before that. So one of them I start by talking about Project 1. I think I did give a reasonable rundown which tells you enough to help you start, but not too much to help you finish. I think it's the Goldilocks of giving answers, right? And the other thing to say is that, I don't really hold official office hours, and I know that that might be a little bit annoying, but basically, if you need help, send me an email or contact me on Discord. If I don't respond by Discord, just send me an email. You don't have to send me two things at once. Yeah, so so there's playlists now. So I think I posted the let me check the Discord. I think I've posted the playlist there. At least some of the lectures should be linked there. Yeah, the playlist is there. It's on the announcements on the Discord. I might just post it to Blackboard as well. Yeah, I'm sorry about that. We're just trying to. I really like the YouTube format, and I don't want to go to Zoom because I'm lazy and I don't really know anything about Zoom and I don't want to do it, right? So I'm making. Yeah, I mean, maybe Twitch. I don't know. I think that they'd have the same problem with Twitch. Twitch saves videos as well, right? You can have like streams that are saved. Anyway, okay. I think that's basically it for. Let me just put the tablet down so that we can start. So, okay. So remember. Okay, so we've done that part. Let's talk about tree deletion, because it's something to talk about. Oh wait, I want the tablet again. So remember when you're deleting from a tree, what you have to do. So you can either find the predecessor or the successor. In most books, the reason why we find the successor is just because of the condition in a tree. Remember, in a binary search tree, where things get inserted is dependent on, like, if this value is 10 and you want to insert 12, say this is 15, remember you have to go right because it's bigger. So if you're inserting 12, you go this way, and then you go this way and put the node in. Well, technically you put the node in down here as the child of 15. And I didn't say the naughty word this time that I won't say, because if I say it, I'll keep saying it. Right? So if you want to insert 12, you stick 12 down to the right, then to the left, and then it goes in as 15's child. And so, yeah, I know. I'm very glad I didn't say it this time. Who knows? So anyway, the reason why we need to do this is because, for instance, if now we insert 10, we would put 10 in here, right? And then this can only be things like 8, 9, 7 here. And so if we find the predecessor, I guess that actually works in this case. But if we find the successor, it's definitely guaranteed to work, because 10 is like the closest value, and we know that the things over here are bigger than or equal to, and the things over here are strictly less, right? And so it's possible over this way we'll find an element that's equal to the node. And so remember what you do. You find the successor node, and then you delete the successor node, right? You move the value up, and then you delete the successor. So remember what a successor is. It's basically the smallest node, right? Smallest value, I should say, in the right subtree. Basically, you could write it as like the minimum value x, such that x is in the if this is like the node n, n dot, where this means in the subtree. See, you can say subtree. This is fine. Okay. So, okay. So how do you find the successor node? What you do is you go right, right? The instructions are go right, and then go left. I should say go right 1, and then go left until you can't. And whatever node you find, that is the successor node. So the predecessor node is the same kind of thing, except that you go left and then you go right until you can't, and that's the predecessor. Now, it's always possible that the successor could have its own child. For instance, if 10 had 11 here, so if and you see that there's no more left, right? There's no more left going, right? You can't go this way. So if you can't go this way, this is still the predecessor, even though it's not the bottom node in the tree, which actually means that what you have to do is if you're going to delete this 10 at the root, then you have to find this 10, you move this 10 up and you replace it. So now this 10 disappears, and then you have to delete this node. When you delete this node, you have to find its successor. Well, its successor you find by going right, and then going left as far as you can, but you can't go left at all, so its successor is 11. And so then you put 11 up into here, and then finally this node is, remember what this is called, this is a leaf. And so because this is a leaf, it's childless. And so then you finally can actually delete a node. So the cool thing about delete in the case of a binary search tree is that at least on the way down, until we get into self-balancing stuff, right now you actually don't really change the structure of the tree until you get to a leaf node. And even changing like whether a leaf node is null or not is not a significant change to the structure of the tree, right? So if this were, for instance, I guess this could only be 7, we can make it 7.5, right? So if this were 7.5 and this were, say, 6, and we deleted 7.5 and you took this off the tree, that's not a significant change to the structure of the tree, because in order to find elements, you still kind of go through the same patterns. Whereas with insertion and deletion, so basically with insertion and deletion, you're only ever really inserting at leaf nodes, and you're deleting at leaf nodes. So this like predecessor business finds the next value down, it moves it up into the node that we're going to keep, right? So this is actually the node that was being quote-unquote deleted, but we're not really deleting the node, we're just deleting the value out of the node, and we're moving a new value into its position. And then finally you're saying, well, okay, now I can get rid of this node, but I can't quite because it still has children, so now run the delete algorithm on this. So, okay. So let's do a little bit of deletion, and then we'll do a little bit of AVL. So let's see what we can add. Remember, here's our BST class. So what do we need? Basically, we need a find node. There we go. And this one is not going to return true or false. It's going to return... and you'll see why we need that. And then in order to make delete work, and we'll probably also want a BST node pointer get predecessor, successor. It really doesn't matter too much. Which node you, whether or not you find the successor or the predecessor. Literally the only reason why we make one choice over the other choice is just because of the operator. It makes it slightly easier in some edge cases. Yeah, the predecessor is the maximum in the left subtree, and the successor is the minimum in the right subtree. Okay, and then the other thing that we might want to add and I'm not sure if we really want to do this, but I'm going to do it because I think it does technically make our job easier. When you're removing things from a binary search tree, it's always nice to have the parent. Predecessor is the less, yeah. That's not complicated, right? So, okay. Okay, so let's put in BST. There we go. And then let's put in BST here. So these should be easy to do, right? To help us find a node, remember, let's do this, instead of recursively, let's do this iteratively. So let's just call BST node pointer p current is equal to p. And I know I remember I called it head. I might create a new binary search tree, or maybe I'll refactor or something and call this p root. We should really. Yeah, it's okay. I mean, the successor doesn't really suck that much, so it's okay. Okay. Yeah, so how do we find a node? Instead of so let's say while p current, right? And p current, is it element? Yep, element is not equal to element. So there we go. And so remember, p current dot element, or p current arrow element, is giving us the element inside the node. This is giving us the element we're supposed to find. So if they are equal, basically, I guess here, if not p current, we can return null pointer. Technically, we could just return p current, but I'm doing that for clarity. And then you say else if, or else return p current. So really, actually, you don't need any of this checking. You can just return p current, because if p current is set correctly to null pointer, so basically either this will be null pointer or not. And you're like, well, okay, that is the true dichotomy. Either something is or it is not a thing. Okay, so anyway, if p current element is, say, less than, no, let's do it this way. If element is bigger than or equal to, I always find it easier just to write the element first, because then the operation is the one you expect. If you flip them, then you have to reverse it, and I always hate doing that because it confuses me. So if the element is bigger than or equal to the current thing, then we're going to set p current. Well, I guess if it's equal to, we break out. So if it's bigger than, we will say p current is equal to p current arrow right. And else, because here this takes care of the equal condition. So if it's equal, we just break out. And when I say break out, I mean we terminate the loop. We don't actually use break. You're allowed to use break, so I guess that's one thing I should say. You're allowed to use break. Unlike in like 201 and maybe 202, I don't know. Are you allowed there? I don't know. All I'm going to say about using break is just like be good, right? So you see how here this loop, when I say break out, I mean that my while condition is good enough that I don't need a break statement at all. So there are certain cases where you might need where you might need to do break in certain things, and I'll show you kind of instances where it might be. If I ever find an instance where it's really useful, then I'll use it. But like generally, if I want to put a break in, my first instinct is that I haven't written my while condition well enough. If I'm sticking in a break, I'm always thinking to myself, like, is there a better way to use while? Generally, if you're doing it in a for loop, you're doing it like for everything in a list, and then if you find that thing, then break out instead of like returning or something, and that's usually okay. Not terrible, as long as the for loop is simple. Anyway, so this should do it. This should find a node. Now, how do we get a successor? So if I give you a node, I'm going to call BST node pointer p right, or let's just call it right subtree equals p current, and then we're going to go while well, first we need to check that right subtree isn't null. So, okay. So this is how you go left as far as possible, and then we just return the right subtree. Now, I guess technically it's possible that will this handle the worst case? What's the worst case? You'll have to tell me what the worst case is. The edge case I'm thinking about here. Oh, will it handle a linked list? Sure. Because remember, I mean, if your tree is a linked list, then basically like either, well, I mean technically when I say if your tree is a linked list, what I mean is that your tree only has every node only has one child. But the thing is, like, it could be to the right or to the left. So for instance, if I'm going to delete this node, then finding the successor in the tree is basically you go this way, and then you go this way, and that's the successor. So you push this back, and then you delete that. So this is a wonky linked list, right? It's a linked list technically, because it has, every node has its, like, next pointer. But you see that the next pointer is actually kind of modeled here. It's left, here it's right. If it's the top node, well, so we haven't written the delete algorithm. If we're going to delete the root, we might have to do some reassignment. So right now we haven't written delete. So, yeah. Anyway. So now let's write delete, and then I'll show you. Maybe you'll be more convinced. Okay. So let's write delete. Where's remove? Is remove anywhere here? There's find. I think I didn't write remove, so let's write remove. So remember, we have this find node function. We have get successor function. So now we're gonna write bst remove, and I forget all this stuff. I think it's void maybe, or I think I made it bool so that if we actually find the element, then we can remove it properly. Did I do that? Let's see what I did. Yep, it's always nice to do that. Yeah, successor is not a complicated bit of code. It's at least I don't think so. I mean, the only thing you have to be careful of that we didn't check here, right? We didn't check that p current wasn't already null, so don't pass null pointer into here. Otherwise, segfault. Okay, so how do we remove something, right? So the first thing we're going to do is call bst node pointer p remove equals find node element. Oh, and p root, p head. Sorry, I keep calling it head because it really should be p root. Does Visual? I'm sure Visual Studio allows me to refactor p. Can I do this? Is there a refactor? I'm sure there has to be. Projects, view, edit, advanced. You know what I'm not going to do right now? I'm not going to be searching through menus. So let's leave it as p head. And that's what I did last time because I was lazy. So this should find the node. So basically, if p remove, well, actually, if not p remove, we can just return false. And so what is this saying? This saying, like, I'm searching for the element 15 in the tree. 15 ain't in the tree. So just return false, which tells the programmer user, it tells the programmer that, hey, I didn't find it. Yeah, I can do find and replace, but I'm always nervous about find and replace because, anyway. So, okay. So now we found the node, right? And so what we're going to do now is we're going to say, I mean, it would probably be fine. There's probably no problem, but I kind of do want this code to compile and not just explode. So, so now what we're going to do is we're, if not p remove, we return false. So this is a little kind of like, I used to always do it the other way. I always used to say if p remove, then do all this stuff. But here, what I'm doing is I'm just kind of like breaking out of, this is almost like a break, right? This is like if not p remove, then I just break immediately here in return. So at this point, you can kind of assume, unless of course you do something wonky, that p remove at this point is not null. Which is great because now we can, remember that was the one restriction we had on get successor, right? Was that you couldn't call it on a null node. So let's call it, so get successor, BST node, pointer, p successor, just to avoid any jokes, is get successor of p remove, right? There we go. So now we have two nodes, right? Now we have two nodes. One is the successor. One is the actual node to be removed. Now, right? There's two cases, right? We haven't checked p remove's children, right? So technically, p remove could be childless. It could be a leaf. No, not a left. L-E-A-F. It's weird how when you're typing you do like homophonic things like that. Anyway, so if it's childless, so what that means is basically if it doesn't have a successor, right? Well, yeah, if p remove so if it doesn't have a left or right child, then what can we do? I could, but the only reason why I'm not going to is because checking the children is literally this, right? And so it's just one if statement. But I mean, you're right. You can write a helper function, like a nice, even a little like inline function if you wanted to. But anyway, yeah, you could definitely do that. There's nothing that prevents it. I'm just kind of, I don't think remove is going to be that long. Like if you realize that here, there's only really what, like 1, 2, 3, 4 lines of code so far, so that's not bad. So if it doesn't have any left or right children, then actually what can we do? So well, so this is where, I mean, you're not wrong. You're totally right. So this is where you want the parent of the node, and you'll see why in just a second. Because if I call delete p remove, because you're like, oh, I'm happy, but who's not happy, right? And this is why I'm kind of showing you the implementation of this kind of stuff, and at least doing some of it myself. I'm not promising you that all this code works, but at least I'm showing you kind of thinking through the individual details that you have to think through. Doing a little bit more than just theory, because the point is here that what happens if you just delete this, right? And think about the parent, right? Like the parent dot p left is going to be equal to p remove still. But p remove has just been deleted, which means that the parent dot p left is actually still equal to a non-null pointer, or it could be p right. So basically the point is here that when this happens, you're going to have an issue. Well, I mean, basically the danger is that actually it might not even be a seg fault, because a segmentation fault happens when you go outside the bounds of where you're allowed, but the heap memory that you've allocated is actually inside of the memory that you're allowed to use. So sometimes, if it hasn't been overwritten yet, which is usually true in your program, right? Like if you just access it right after you delete it, it hasn't really been overwritten. You can actually still find the data there, right? Like literally you will still be able to get to this node. And then of course you might go to the next node, and then that might be a seg fault, or you might go to a null pointer. So you might actually be able to like find deleted nodes in a tree if you don't set the parent dot left or parent dot right to null pointer. So yeah, so it can be really confusing if you're not careful, because like the heap stuff is inside of where you're allowed to access. So now I know that we haven't set the parent or anything, but we're going to pretend like it works. So p remove is equal to p remove dot p parent dot p left. Then, and of course we should move this delete statement to the end, because we should not be deleting yet. So parent no, not p left, p parent. That's fine. So if this is true, if p remove is equal to the removes parents left, right? So that's how we do it. We go up and then back to the left. And so if that's true, then well, what do we do? That's a good question. So well, we set this to null pointer. And there's an edge case I'm not dealing with right here, but maybe we'll have to understand it in just a second. Else, well, I'll let you do else if everything is the same except it's p right. And so here, we're gonna set this to p right. P right is gonna be null pointer. And then what's the last edge case that we have to deal with here? The last edge case is that we have a root that has no children, right? If you have a root that has no children, then we're deleting the quote-unquote the root node or the head, p head. So if we're going to delete p head, then we should set p head equals null pointer, right? We're actually deleting the head node. So really, actually, we should probably put in something like, if oops. So the first edge case, let me actually just draw it out. So, so when you're deleting a node, right, basically what you're going to have to do, so here is the case where we're deleting a node, and like it could be part of a bigger tree, so here's the rest of the tree, right? But we're actually, this is the one we want to kill this node, kill this one. And so in order to get rid of this one, we see that it doesn't have any children. So what are we going to do, right? We're in the case where we're talking about, we could just delete the node, but then remember that the parent will still have a pointer to this deleted node. So that's why what we do is we check to see, we go back up and we see, hey parent, look at your right node. Are you me? Right? Like basically you know, if your parent has two children, you know, you ask parent, who is in your left hand? Who is in your right hand? And so we ask the parent, who's in your right hand? Is it me? And the parent says, no, you are not right. And so then we're like, parent, am I left? And parent's like, yep, you are my left child. And so if it's left child, then we know, okay, set me to null, right? Forget about me. Because as soon as you set this one to null, then you can delete it, right? But if you delete this and then you can either delete it and set it to null or set it to null and delete it, as long as you have both the parent and the child node somehow saved. There's a bunch of different ways that you can do it. The only thing you can't do is just delete the node and then not set this arrow to null. Because if you don't set this arrow to null, the parent remembers its child and will tell the rest of your program that it's still pointing to something. So those are the two edge cases that we're talking about. Okay. So if the thing is if it doesn't have any children, then that's the case. So, okay. So, what if, and so this is another edge case. So what happens if, so how can this happen? How can it happen that we have some children, but we don't have a successor? Right? So let me show you the case where that can happen. Yeah, so in the BST, we have a parent node. We have like a node arrow p parent, which we haven't created it in our BST implementation, but we're just going to assume it's all in there and working from like the insertion method. And then remember that the root node will just have a null pointer to its parent. So that's how you can tell that a root is the root is the root node. If you just place somewhere randomly in the tree, you can always scan up the tree until you find a node who doesn't have a parent, and that's the root. But yeah, each node has a left pointer, and it has a right pointer. I don't like the red. The red's too aggressive. There we go. Each node has a left pointer, a right pointer, and a parent pointer. And you don't really need parent until you start doing deletion stuff. As soon as you start messing around with the structure of the tree, which deletion does, then you need to know who the parent is. And we'll see that in AVL trees, we also need to know who the parent is. Okay? So when we get to AVL trees. So, okay. So the other two cases, and I'm not sure how much I really want to go into this because I've spent a long time on this already. But let's just finish this up as quick as possible. So if we don't have the successor, then what that means is that there's nothing to the right, but p left, like the p remove dot p left is has something, right? And so what we want to do here is basically, so since there's no successor, you can basically prune that node out and just like relink, right? So what you can do is you can say like the p remove that p parent dot p left is equal to p remove dot p left. And of course, we don't actually know. We would have to check again. So here we have to check if then we do it this way. And then we check to see if it's the right child of the parent. And I mean, if it's neither the right child or the left child of the parent, then we're kind of in some kind of confuso world. So okay, so this is a silly case. This is a case where basically what ends up happening is something like this, where, for instance, like here's the node we're going to remove. Here's the parent. And the thing doesn't have a successor, but it has a bunch of stuff in its left tree. So no successor. And so the idea here is if you're going to delete this node and there's nothing over here, then you can actually just delete this node and move everything else up. And you see that it doesn't break the property of the binary search tree because this node has to be bigger, or I'm sorry, this node has to be less than this node, so that like if this node is 10, this node might be say, this node has to be bigger, so it has to be something like 15, and this node has to be like 8, and this node has to be 6, right? And so because of all that, if you move up 8 and 6, so we put 8 here and 6 here, and then we don't worry about this, then the good news is that this is still a binary search tree because all of these nodes are still in the correct order. Did I forget something? No, I think we're good. I think this is right. Yeah, this one is wonky, but I think it's right. You'll have to think about why that's right, and maybe it's wrong. Maybe it's actually a bug. Okay, and then here's the general case. So the general case is that this thing has, It has a successor, right? Finally, we get to the main case, right? It has a successor, and therefore, and children, right? So what you get to do is then what you basically get to do is, well, what do we do? Well, if it has a successor, then we copy the node's value into, so we go p remove dot element is equal to p successor, dot element, right? And then you will have, now you delete the successor node. So what you're going to do is you're going to go p remove arrow p right. So and maybe you'll even need a delete helper. Actually, we should probably just say p successor. And of course, delete helper doesn't exist. So yeah, I mean, you can kind of, so this is actually a recursive delete function. So these are the two base cases where you don't have children. So this is a base case. This is a base case where it doesn't have a successor. If it has a successor, then yes, you actually do have to delete it recursively. So the answer is yes. can you do it non-recursively? I think you might be able to, but it's a little bit more annoying to do it that way. And so in order to write the delete helper, you see the problem with delete helper is that delete helper has to take a specific node rather than just, so delete helper might even just be, we might end up just creating a delete helper and copy pasting almost all this code into delete helper, basically. But I think that's where I'm going to leave it, because, and I know that we haven't created, let's just at least get rid of the red. Something like this. And then, well, I guess if you've already found the node, then you can actually just make this void. So, yeah. But anyway, so that's where I think I'm going to leave delete, because I've used up a huge amount of class time on it already, and I do want to talk about AVL trees. So I might finish this up, outside of class, or might just do something else about it. But yeah, for now I will just leave it here because I want to move on. But I think you guys have the general idea, right? Basically, most of delete is edge cases, right? Where you don't have children or you don't have a successor. And if you do have a successor, then you do this. And then finally, once you get down to a node that doesn't have children, you can delete that node, right? This is the only time when you delete, when you don't have children. Actually, no, yeah, I'm sorry. You delete here. Delete P, remove here. So anyway, so that's basically, that's my version of delete that I just randomly written here. So is this the best version of delete? Probably not. I mean, if we wanted to optimize it, we certainly could. But anyway, I think it kind of gets the point across that you look for the successor, and then you basically have to check all the different kinds of things that can happen with the successor. Either it has no children, or it has a child, but only a left child, not a right child. And you're right, or I'm sorry, either the node has no children, or it just has a left child where you can just remove it, or it has a successor node, and then you have to do other stuff. Okay. Actually, I think this is basically done as long as we wrote delete helper, where delete helper is essentially copy-pasted version of this. So it's not so bad. It's not so bad. Okay. So now let's talk about AVL trees. So remember what's the problem? Like, why do AVL trees exist? And so the answer is because the worst case of like an unbalanced BST is something where it's basically a linked list, right, of some sort. And I'm not saying it's, so I'm saying it's kind of something like this, or even something like this with like, which is not quite a linked list. This is essentially still the worst case, because I mean, yeah, you could stick this on, but it's only one more node down. The problem is that the height of the tree is like theta of n here, right? It's if the height is strictly bounded below and above, so it's like some constant times n, then that's a problem, right? Because generally, the promise that a BST makes, a BST says, I promise. Searching is log time, right? Log n time. Technically O of n log time, and deletion is O of log n time. And what else? Finding, right? Well, I guess finding is the same as searching. Insertion is O of log n time. But you see here, that's not true, right? In this unbalanced BST case, the problem is that actually they're all O of n, and they're bounded below by n, so they're both O and omega of n, right? This means they're bounded below. So that means that they are no better, right? No better than n, and this makes it bad, right? Now, being no worse than n is not really a problem, because you could be like, oh, constant time is better than n, so no worse than constant time is no worse than n. That's true. Log time is no worse than n. That's also true. But here, if it's no better than n, then that can take a long time. And usually in binary search trees, you'll end up storing like 1,000,000 elements, right? And so to take 1,000,000 elements rather than something, some constant times 1,000,000 time, rather than some other constant times log 1,000,000 time, right? So remember, with logs, what happens, this 6 comes down, so you just get 6c twiddle log 10, and so this, whatever constant c is, as long as this constant is reasonable and kind of probably similar to this constant c, you see that this is going to be significantly superior, because log base 2 of 10 is like, what? It's like 3 point something. And so this will give us 18 times the constant c. This gives us 1,000,000 times the constant c, right? So 18 c's versus 1,000,000 c's, right? And whatever c is just like basically whatever constant comes out of the fact that you're running it on some fixed computer with some fixed memory with some processing speed, and all the other stuff about how the algorithm is running goes into that constant c to give you the time. And so it's probably going to be pretty similar to this constant c. It doesn't have to be necessarily, but since they're the same kind of tree structure, it will be. But you see that this 18 is nice and small, and 1,000,000 is big. And so that is the whole idea of data structures. Data structures is like, can we get it to be this one and not this one, right? Like this is okay. This is really bad, right? You don't want to be doing, especially if you're writing like a database or something like that, you don't want to be doing 1,000,000 queries in order to find one data element, because then this is not the internet, right? Internet cannot do this, because what this means is that your queries would wait a few seconds while they search databases, and the internet would just explode if databases were this slow. And so this is why you use some kind of tree structure, some kind of hash table, something to improve the performance of your algorithm. So, okay, but the BST promised that we could do log n time. So let's look at what AVL does and see if we can guarantee log n time using AVL structure. So what is the AVL structure? Come on, tap. There we go. So the AVL structure is that every node has a parent, it has a left, it has a right subchild, set it. So it has a left, it has a right child, and then it'll also have an element, so the data element, and then it has one other piece of data inside of it. It remembers its height. And so you might say, oh, well, that's cheating. Like, why should a node in a tree remember its height? And I agree with you. Nodes in trees should not know anything about their position, but that's not the way AVL works. But the AVL rule is actually very simple. So red-black the red-black rules are simple, but the implementation is really freaking complicated. On the other hand, AVL tree structure is very, very simple, and its implementation is simple. Okay, I guess I shouldn't say simple, I should say simple. So the rule is this. heights at any node can differ by at most 1. So of course a height can, and we'll just say absolute value, right? So basically what I mean by that is that the height of the node dot left minus the height at node dot right. And let's put this in absolute values, just so that if this is 0 and this is 2, then this will be -2. Absolute value of -2 is +2. So that would violate this condition, right? So I don't care if it's the left node who's heavier or the right node who's heavier. We're sticking it in absolute values so that if this node difference is 2, it's too big. And if it's -2, then it gets absolute value, and now it's still too big, right? It's so the only possibility is basically a tree structure like this. So this is okay because this has a height. Well, let's just say that this guy has a height of 0 because it's a leaf node, and this node will have a height of 1, and the null pointer here, right? So because it's a null pointer, we'll call that a height of like maybe -1 because it's a null pointer. So let's actually look and see and just look at some structures. So here, if you have this tree structure, is this an AVL tree? And you're like, well, clearly it's not. And the reason why it's not is because this guy has a height 0. This guy has a height 1. So how do you calculate height, right? Height of a node is equal to 1 plus the maximum of the heights of the left child and the right child. Okay? So basically what you do is the height of any given node is the height of its children, the maximum height of its children. So like here, both of these children have heights -1. So this one has a height of 0 because it's 1 plus -1. This one has, so remember that this, these -1s are really null pointers. So the reason why this has a height of 1 is because its children have heights of, oh, yes I am. Let's see. No, I don't want to move the entire window. I just want to move my head. There we go. I don't want to move the text, so there we go. Let me actually just type that. So like the height of a node is equal to 1 plus the maximum of the height of the left child and the height of the right child. And now we don't have to look at this ugly, terrible, terrible, terrible writing, which I, did, because it is terrible. Okay. All right. It might be, yeah. And so here you see that this is where the max rule comes in, because here you're saying this one has a height of 2, and the reason why it has a height of 2 is because the maximum of these two is 1, and so it's 1 plus 1. Okay, so this is not AVL, right? Because here you see a violation, right? You see that this has a height of 1, this has a height of -1, so this is not AVL. Like an array. I'm not sure. I don't know. So, okay, let's calculate that. Let me draw a more general tree and we'll calculate some heights. There we go. There's a tree. Let's calculate all the heights. So all these leaf nodes are going to have height 0. And then remember that this is the maximum, so here's 1, 1, 1. So at this point, it's actually all AVL. It's okay. And then here we have a height 2, and this is a height 2. And then here we have, this is height 3, and then this is height 4. Oh, no. So, yes, so so basically there's only one way to fix this. Well, okay, so the first question is this an AVL tree? Of course, I've written under my head again, but who cares? AVL, is it AVL? The answer is yes, because you see here this differs, these children differ by 1, these children differ by 1, these children are 0 and technically -1, so they differ by 1, right? This is actually a null pointer. Here we have things that, so, okay, actually, oops, so this is where it breaks. So this is not AVL here. But we can actually fix it, all right? So let me show you how we fix all of this stuff. And the way is that you don't build your entire tree and then AVLify it. That's not how you do it, because that would be really complicated, and you don't necessarily know how easy it would be to convert an entire, essentially randomized tree into an AVL tree. The point is that you do it on every single insertion. So for instance, let's just do a simple case here. Let's say that you start with this tree here. So we start with, say, 10. Let's say this is the node 10, and this is the node, let's just make it 5, just so that we have some nodes. And we're going to insert the node 7. And so here what we're going to do is we are going to put 7 in its place. Okay, so at this point, right, the heights are, everything was AVL until we did this, right? Because we said, you know, this node had height 1, this node had height 0, and this one had height -1, and so this difference is okay. But now we have to redo all the heights. So here's what we have to do, right? We have to go up, and so what we say is, okay, I'm going to be height 0 now because I've just been inserted into the tree. So now I'm going to update my parent. So now when I pop back up the tree, I have to update the height of the parent. And so now you see, okay, does this break anything? Well, this has a height of -1 because it's null pointer. This height is 0. So these are 1 different, so they're okay, right? So this, up till here, we're okay. Now the problem is that we get to the parent and we see that it is 2, right? So the height of here is 2. That's not the problem. The problem here is that this 1 and this -1, right? Because 1 minus a -1 is equal to 2, which is not less than or equal to 1, right? So this breaks the AVL property. So now your question is like, okay, how do we fix it? And so wouldn't it be nice? Let me color these nodes so that they're good. The new node that we've inserted, I'll leave that black. The parent is going to be purple. And the grandparent is going to be green. Green for grandparent, P for purple. So this is what we're going to do. We're going to do a rotation. And so let me show you what I mean by a rotation. We are going to rotate everything this way. And so maybe this had a parent, maybe it didn't, we don't know, but this is what we are going to do. We are going to rotate so that 5 is now the top node, the root node in this subtree, or the parent node, or whatever you want to call it. So 5 is going to be the top node. And then 10 is going to be the new child on the right. And oh, I'm sorry. That ain't right. Let's do it again. So this, I was intending to do the other rotation. So this one we actually have to do 2 rotations. The first thing we have to do is we actually have to rotate this way. So let me show you what I mean by that. We have to say that this one is, we want to get it into this configuration. And let me show you why we want to get it into this configuration. So, so if we put a purple around here and a green around here, then the question is, have we broken the tree? And the answer is no. And let me show you why we haven't broken the tree. Because remember, 10 is still the root node. We haven't messed with that yet. All we've done is we've rotated this way. There's nothing over here. So 7 becomes the parent and 5 becomes the left child. Okay? So 7 becomes the parent, 5 becomes the right child. And then what we get to do is we get to do a second rotation this way. And so now let me show you what happens when we rotate this way. We will get 7 as the parent, and then we get 10 here, and we get 5 here. At this point, you say to yourself, wow, wait a second. If we count the heights of all these nodes, this has height 0, this has height 0, this has height 1. Oh, this is AVL again. Okay? So that is an AVL tree now. Okay? So, and then the only thing that you have to do is actually you have to go back up and you have to check the next level. So it could be that the next level here has a height 3 and a height 1, and so you might have to do other rotations or something. But I'm going to leave that off for now because I want to go over the other cases. So basically there's 4 cases in an AVL rotation. The 4 cases are these. Either you can have an imbalance like this, you can have an imbalance like this, you can have an imbalance like this, or you can have an imbalance like this. Okay? So those are the 4 imbalances. And the answers, so you update the heights after every rotation? Absolutely, you must do that. Because as you go back up the tree, as you go back up the tree, you then check the parents and the parents and the parents and the parents to make sure that they all have the right heights. So let me pull up the AVL tree visualization, but let me just, before I do that, let me show you that basically here, what we're going to do is we're going to do a rotation to the right, and so this will become, well, let's actually like color these nodes. So what happens in this case is we get a tree that looks like this, where we have a purple node. Let's make the purple node always the grandparent, and then the red node will be the parent. That way we can see what happens when we redraw these. So, okay, so this becomes the parent, and then this becomes the left child. So this is what happens. In this case, we actually do an intermediate rotation. First you rotate this way. As I showed you, you kind of put the black node in here, and then you will rotate another time. So here you'll get the black node on top, the purple node here, and the red node here. And it's the same thing in this case. You have to do an intermediate rotation here so that the black node... So if it's like all left or all right, it's easier. If it's left right or right left, it's a little bit harder. You have to do like an intermediate rotation where you get something like this, and then you'll have the black node on top. And I guess in this case you'll actually have the red node on this side and the purple node on the right side. And finally over here you just do a rotation so that red is on top and purple is to the left. and black is to the right. So these are all the different cases. Yes, height is, as I said here, basically, or let's see, I think I drew it out somewhere. Where did I say it? Yeah, so basically, every node has a parent, it has a left, it has a right, it has an element, and it has a height, right? You must keep track of this height. Okay. All right, so here are our 4 cases. Let's actually watch a little bit of this happen. So there's that visualization online, which honestly I kind of want to make a new one of these, but like this one is actually pretty good. So let's insert a few nodes. Let's insert 50. Okay, cool. Now let's insert 25. And you notice here that they are keeping track of the heights, and they're calling this height 1 instead of height 0, but it doesn't matter as long as you're consistent, right? So that's always the question, like is a single node a height 1 node or is a height 0 node? Who cares? As long as, remember here then, the null pointers here will have height 0s then, instead of height -1s. So let's insert 12, right? So 12 is going to go, let's reduce the animation speed just so it doesn't go so fast I can't even say anything. It's going to insert itself here, here. This is standard tree insertion. And then it gets to the grandparent and says, wait a second, the heights are imbalanced, and it rotates. So now let's insert 75. So 75 is just going to insert. Because if you notice here, this is height 1, this is height 2. There's no violation of the AVL property, right? 1 or 2 minus 1 is 1, so that's okay. Now let's insert 80, right? Let's violate the property again. No. Let's insert 65. The reason why I want to insert 65 is because I want to go right, left. So let's insert 65. So we insert 65. It'll go and become the left child of 75. And then you notice here, this is one of the alternating conditions. So, right, and so that did it very quickly, but you see what happened, right? Let's insert 65 again and do it even slower. So here it's going in. It's going to become the left child, and then here, just watch very carefully. It's going to rotate this node up, and then it does both rotations in one visualization step, which is okay. It's just very quick, right? So, so what we started out with was, we started out with this condition, right? Purple, red, black, and so then you end up with black on top and purple to the left and red to the right. And so let's check to make sure that that actually happened, right? So let's do it one more time and just make sure it happened. And if you guys want the visualization, it's right here. So this is the, let's see, let's pause this for just a second. The top node is purple, this node is red, and this node is black. And so what we want is that this node will become the left child, this node will become the right child, and the black node on the bottom is going to go all the way up and become the parent, right? So, and you notice the height imbalance here, right? The height imbalance is because this has a height of 3 and this has a height of 0. So that can't possibly work, right? So we have to do a rebalancing operation. So now it's going to do it. There we go. Now everything's fixed because it works. Okay, so now let's insert 95. And see what it does. It should insert here. And so at this point it's balanced, it's okay. And then now it's, okay. So, okay, that was too fast. I couldn't say that. I couldn't even vaguely say that. So let's insert 95. And then we got to slow it down when we get to the right place. So here it's going to be okay. And so why is it okay here? Right? It's okay here because this has a height of 1, this has a height of 2. This has a height of 1, this has a height of 0. So 1 minus 0 is okay, 2 minus 1 is okay, but when we get up to the root, we're going to update the height of the root. So we're adjusting the height after the recursive call. The height of the root is 4, but that doesn't actually matter. The height of the root is only important if there's a node above it, which there isn't. What matters here is you notice that the height of this subtree is 3, the height of this subtree is 1, and 3 minus 1 is 2. So that is not right, right? And so basically what you're going to do is then you have to do a rotation. Now the question is, what rotation are you going to do? And so the answer is, right, you have to kind of figure that out, like what case you're in. And in this case, you notice that here, they just do a single rotation to that direction, and so to the left. And then I think it's done. Yep. Are AVLs printed in traversals as well? Sure. I mean, so the thing is, like, a binary search tree can do a traversal, and an AVL tree is a binary search tree, right? The thing is that after you do all these rotations, an AVL tree is always still a binary search tree. And so that's one of the things that we might have a homework problem on. I think it's really important to realize that, is that every time you do one of these operations, the reason why these operations happen the way they do, the reason why rotations are designed the way they are, is because you notice 65 is smaller than 75, bigger than 25, and 50 is in the right place, 12 is in the right place. Like, if I just ask you, is this a binary search tree, you would come back with yes, because all the nodes are in the right places. Whereas, like, if you didn't have the nodes in the right places, then you could have a real issue. So let's insert 112 and just see what happens. So this is a right distinction. Are we going to do anything with AVLs, red black trees on any projects or tests? I don't know. Usually project 2 is some kind of tree project. Now, they haven't done a lot of self-balancing stuff. Sometimes they do splay trees, sometimes they do other things. So I don't know. So it depends. It really depends. But it could happen, right? Project 2 could be a self-balancing tree. Project 3 could be some kind of splaying heap or something like that, like a leftist heap or something like that, and you might see some kind of splay operation. So here now you see an imbalance, and so here the imbalance is that is a right imbalance, and so now it's just going to perform a single rotation where 95 becomes this node, 75 goes down to the left, and 112 comes up. So let's do that. There we go. And so you see that this is actually producing for us a very close to perfect tree most of the time. AVL insertion functions will include a height increment and check for balance. Yeah, so what you do is the AVL insertion does regular BST insertion on the way down, right? So I don't care about the AVL property on the way down. So for instance here, you're going to notice, like, if I insert 87 and I just play this thing, it doesn't care, it doesn't check anything about the heights, it just sticks it in. And then at this point, then it detects a height imbalance, right? Actually, it doesn't, because it's okay. And it doesn't here either, because 2 and 3 are one apart. Okay, so we still have to do something else. So let's insert 89. Now let's make a height imbalance. So inserting 89 is going to give us a height imbalance. So here we go this way, this way, this way, all the way down. And at this point, you see that this is just a binary search tree, right? We've broken the AVL property, and so the fix-up happens on the way back up. So you insert on the way down, and then as you go back up, then you have to check the AVL property, okay? So there we go. And then here you see that now 1 and 1 are equal, 2 and 1 are only 1 apart, 3 and 2 are 1 apart. So as it turns out, this is re-AVLified, right? So this is an AVL tree again, and now we're happy. So we can go back up, and we get to the root, and we're done. So I think that's all I have for you today. We will do a ton more AVL stuff. Might even do a little bit of AVL insertion next time and AVL fix-up. We might do, and then we'll do AVL deletion, I guess, very quickly. AVL deletion is a lot like insertion. Basically, you delete as usual in a binary search tree, and then you do a fix-up. So that's the point about all of these things. You always have to do the binary search tree operation on the way down, and that preserves the binary search tree operations or the structure. And then on the way back up, you have to ensure that the thing is still an AVL tree. So you have to do rotations on the way back up. So hopefully this made some sense. I doubt that at this point you'd be able to like fully code an AVL tree, but that's okay because we have one more day on AVL trees. So, all right, I'll let you go now. Hopefully this was at least interesting. Yeah, okay. Have a good rest of your day. Am I able to code one? Probably. So I'm going to say not in class. Like, probably not in class. Coding an AVL tree may take, like, 3 hours. If I'm going to explain, if I'm going to explain everything. Maybe if I do it, maybe if I do it, I'll do it, separate video. Yeah, all the videos, so go to, Discord, announcements. So it might just be like an extracurricular thing, and I will just like tape it and put it up. It won't be an official lecture. It'll just be me talking, and if you really want, I might even tag it with like, here's where I do the insertion part, here's where I do the deletion part. But it's going to be huge, right? Red Black it would take me like 2 or 3 hours just because, let's be honest, I will introduce 100 bugs into my code, and it will take me a while, especially if I actually have to make it work. It will certainly take me a few hours to get AVL trees and Red Black trees working perfectly. Okay, well that's all for now. I'm going to run the outro, and then if anyone needs any help, I'll be around on Discord, etc. Alright, bye guys.